is Jorge Santos, and I'm a senior research engineer at Embark Studios. Today, I'm going to talk to you about physics-based animation of arbitrary creatures through reinforcement learning. So, let me start with the premise. And the premise is that we want to build a virtual world. In this world, everything is interactive, and users have to be able to interact with it physically. Users can also change the world around them and remix it and create new things. So in this context, also, we would like to populate it with intelligent life, or some sort of intelligent life. And we arrive to the objective of this talk, which is to allow anyone to create living creatures and play with life. The play with life here emphasizes that they have to be able to interact with them physically. So we make this public, and a little girl that saw our stuff come to us saying that she wants to create a living lizard. And the question for you guys is, how do we do that? And think about this for a minute. Some of you, being game developers, might say, come on, we know this stuff, right? We have been doing it for years. We just, start by creating the lizard assets, then we rig it, then we just give it to a couple of our animators to spend some time animating each movement, and voila, right? If you would be thinking that, then you would be missing one essential point, that it has to be physics-based. So yeah, okay, no problem. We do the same thing, and then we just use inverse kinematics, so something similar to transfer the movement to the physics realm. And, we just fine-tune it until it looks right, maybe add some forces here and there. And if it stumbles or falls, maybe we just add a few imaginary forces and to make it stay upright. And this is it, right? Okay, let's do this. And we do this, and then some more people saw our stuff and come to us saying, okay, now I want a biped, another one wants a dragon, another one wants blah, 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 and we're starting to sweat here. Right? Why is that? Because we have to face a harsh reality that animation takes a lot of work. Typically, you would have to animate each single movement, or you would have to record it as a motion capture in some studio, and then you could schedule each animation given some events in the game. But this workflow, it is clear that it doesn't scale to multiple creatures, unless of course you scale your team of animators. And the girl is calling again, and now she says that the lizard that we gave it to her, she threw a box at it, and the lizard just kept walking doing exactly the same. Of course, because we forgot to do the animation for the lizard to react to the boxes. Yes, why shouldn't she throw a box to the lizard? We told her that she could do anything in this physics world, anything physical, right? And then she also said that in a hill, the lizard keeps walking exactly in the same way and doesn't adapt to the terrain. Oh yeah, we also forgot to create the animations for the lizard walking in uneven terrain. And the problem with this is that this workflow wouldn't be truly reactive either, unless specifically programmed to. If the range of the interactions in a physical world is unbounded, then we would have to think of an unbounded number of things and make an unbounded number of animations to react to each specific thing. So I think it's safe to say goodbye to these amazing emergent interactions that we were looking for. And we shouldn't also forget the anyone in the equation. We cannot assume the little girl to know anything about animation or about game design or about programming. We cannot delegate our work to the final users. They should just be able to create freely and play with their creations. So, okay, let's try again. How do we do that? And I don't mean to hold the absolute truth, but I am going to tell you what we think is the solution, or at least our solution. That is that we allow them to learn. Enter Lizzie. Lizzie is our representation of this dream of an arbitrary creature that can take life and start to walk. It's a simple lizard and it's easy to experiment with. So what is Lizzie? Lizzie is essentially a set of collision shapes and primitives stacked together by physical joints. So you can think of it more like a robot. A robot in which each arm, to move it, you would have to apply a force to each of the limbs instead. And our objective in this context is to go from something like Lizzie to a compelling way to locomote herself. And remember that we can no longer just move one arm from one place to the other. We have to think of the force that we'll need to apply to the arm. So if you think about it, the problem is no longer really that close to animation, right? And it would be in a way closer to robotics. And in many ways, actually, it's literally robotics what we're doing. Think that for a creature to walk from point A to point B, now the creature also would have to balance and not to fall. We didn't have that problem before, right? And it's a hard problem on its own. So clearly, Lizzie will need some sort of brain, right? Some sort of controller that dictates which is the correct action to do at every time step, since we are dealing with physical forces. And how would this brain work? Let's try to sketch it out. Let's separate the mind from the body and try to sketch at least what we would need to make this work. Okay, so the first component, what you would first need to do is to gather all relevant information for the movement. Essentially, just like us, if I want to move my arm, I need to know right now where my arm is and where do I want to move it, at least, right? So there is, at least there are a few numbers of features that we will need to gather before we think of moving something. This is the observation. Here we put things such as the positions of each body part relative to the root, the orientation of each of the joints, if something is colliding with something else, where do we want to move, maybe an observation of terrain. Just gather everything that you think that will be relevant for movement and stack it essentially in a list of floats. You don't have to worry about the particular position of each item in the list, just stack it everything in a list of floats. Okay? The next step would be to pass it through this brain of ours, which would need to take that observation, that information, and make some computation inside so as to prescribe the correct action for that observation. And here the actions are very primitive, are essentially where do you want to move your elbow or each joint in the next frame. And then we let physics do the rest. Essentially like a spring, right? If you want to move it here, then you let physics do force to move it there with certain kind of controllers. And then we perform the action in that frame and we step the world and we do the same. We observe it again and we pass it through the brain again, creating essentially a closed loop system. So now let's focus a bit more deeply in the fancy part, the brain here. What is it and how do we do it? Well, as I told you, the brain is something that would take a list of numbers in one side, and then it would do some computations and output another list of numbers, which are the actions. So essentially, if you think about it, is an input-output relationship, right? It's associating each action to one observation. And thinking about it is very general. An input-output relationship, if you think about it, is pretty much any computation that you can think of. For example, the square operation. That is an input-output relationship which associates to every number in the input with its square in the output. That is an input-output relationship. Or, for example, the sum operation, which associates to every list of numbers with its sum. But today, I want to talk about a very special kind of input-output relationships, which is that of neural networks. Neural networks are input-output relationships, just like the others that we have discussed, but it's a very special kind of input-output relationship. As we said, in the input we have a list of numbers, then some computations happens, and we have a list of numbers in the output. But a neural network has parameters, and those parameters are essentially the arrows of the network, which will multiply by some numbers or by some others. Changing those parameters would change the actual operations that the network does. And this is special because a neural network can essentially become any input-output relationship if you find the right parameters, the right arrows. A neural network can become the square operation, or it can become the sum operation as well. Or hopefully it can become the brain operation that we were describing, which associates the right action to each of the inputs. The question here, of course, is what are the parameters which achieve that? Which are the parameters that turns this box, this network, into a brain? Well, to answer that question, we need to talk about reinforcement learning. Reinforcement learning is a field that allows us to calculate those parameters which transform this meaningless box of a neural network into a useful controller, which is the brain. But first of all, to start talking about reinforcement learning, we have to think about right. What does right means? We're saying that we want the right action at every observation. What is right? Everything starts with rewards. And essentially, you will need to define a reward function. A reward function is some incentive that you're giving your agent to learn. It's essentially a function that takes in an observation and an action and then evaluates frame by frame if it was good or it was bad. So think about this as incentives, as cookies. Why not? For example, think about it. We can think about this function that would incentivize a creature to walk towards a goal, which is the function that we actually use in our world. So I will give you 2 cookies if in this frame you get a bit closer to the goal. I will give you 1 cookie if you face the goal in this frame. And if in this frame you have fallen, I will remove 100 cookies for you. And if you reach the goal, I will give you 200 cookies. So you can imagine that if a creature wants to achieve more cookies, it will have to perform according to our desires or incentives. So it's all about maximizing the future rewards. Or in other words, it's about maximizing how many cookies you're going to get in your lifetime. Just like life itself, right? And we're going to call this value the value. You can count how many cookies you are estimated to win in the future, and let's call that value. So let's try to sketch a bit how it would work. We start in one position, observing one observation. Then we would pass that observation through our brain that doesn't need to be good, already. It can be just a random function, but we pass the observation through our brain to see how good it does. Then the brain prescribes an action, and we take the action, and we are in the position to evaluate our reward. So we get R0. Then we step the world. We are now in a different position. We observe a different thing. We pass it through the brain, and we perform a different action, and we get another reward. And we do that for a number of steps into the future. So given this simulation of the future, how good is this brain? Well, as I told you, you just sum the rewards that you get in your lifetime, and you get the value, which is our way to evaluate the brains. Here you will notice a gamma parameter that is to wait time, because one cookie is not worth the same today than in a million years, right? So that's essentially what it means. What we want is to change the parameters of the network in order to maximize this number, the value, to maximize the sum of future rewards. So how do we do this? Because if you think about it, we cannot just try different brains and simulate each of them for 1,000 steps into the future. That would be a bit costly, right? So we do it using a paradigm called actor-critic algorithms. In this paradigm, we have one network, which is the network that I've told you about, is the brain. In this network, we input an action and it produces, we input an observation and it produces an action. And we're going to call this network the actor. And then we're going to have a different network that we're going to call the value network, whose task is essentially to estimate how many cookies we're going to get into the future, how many cookies the actor is going to get into the future. So if we are starting with a very bad brain, a very random actor, the value will still be low, but the value function will be in charge of predicting how low. So now if we manage to achieve this task by training the value function, we said that neural networks are essentially malleable input-output relationships, right? So we're going to train this network to do that. If we manage to solve that, then we have one way to very quickly evaluate how many cookies am I get in the future. That's why it's called the critic. And once that we have that, we can make them interplay. The value function will be constantly trying to estimate the value that the brain, that the actor will get, and the actor will maximize those actions which the critic tells that are good. So since we have a critic which is already kind of trained to predict the value, then the actor has just to maximize those actions to encourage those actions which achieves a good critic. And we could be talking about this the whole day, pretty much. So this is as far as we will get with reinforcement learning. I just want you to remember three things. The first one is that we parameterize decision policies, or brains, with neural network. The second one is that we need another network, the value network, to estimate the value of future rewards, to train the brain, and we make them interplay together with an algorithm called soft actor critic, or SAC, is the one that we choose. If you want more details on this algorithm, I refer you to the paper by Harnuj et al., which is brilliant, and you can find a lot of insights there. Okay, so let's see some results. Let's see all of this in action. First of all, Lizzie would start learning, right? Lizzie would start with a random brain and would perform random actions. But in this time frame, the value function is learning which of those random actions lead to good rewards in the future. So in a little bit of time, we would see the brain adapting to that value function, which has already learned which actions perform better than others, and will start to encourage those actions. And in not so much time, we would start to see Lizzie performing sensible actions for our task at hand, which is to locomote itself towards the goal. We also use a lot of Lizzie's learning together. In this example is 30 agents learning together, and we are gathering observations from all of those. They use identical branch at each time step. And in around 4 hours, give or take, we would see Lizzie locomoting itself reliably to the goal, which is what we wanted. But it's not all about Lizzie, right? Remember that I told you that this was about arbitrary creatures, that doesn't have to be Lizzie. So to show you that this is not just ad hoc of Lizzie, let me show you some other user-created creatures. For example, here you have a seal. A seal is a creature created in the same way, a set of primitives joined together with the form of a seal. And we try to get the anatomy and the way that it can move right. The rest is just the same button. We play the same button, we run the same algorithm, and this is what happens. The seal learns to locomote itself in a manner that is very similar to reality. Look at that turn. Get the anatomy right, and the gait emerges. If you ever wanted to see how a hand would locomote itself, well, here it is. Therefore, in this framework, animation is no longer the starting point. It's an emergent property of the anatomy, and we have to have that very clear. And another creature that we're particularly proud of is a biped. Why? Well, think about it. For bipeds, there are just much more ways to fall than the ways that there are to walk properly. We are very unstable creatures. And typically in the literature, the way that train bipeds, they would need a very more complex algorithm, or they would use additional data. We wanted to train it exactly with the same framework, essentially pushing the same button. And this is what we did with a little bit of love, I have to confess, in the reward tuning and more time of training, but this is what happened. Here, the biped is a bit asymmetric, as you say. These were the first results. I will show you better ones later on when we correct this. So this is great. And you might start to wonder, what happens if I change physics? Definitely it's a question that we asked ourselves. And if you have this kind of technology, what's one of the first things that you think of doing? Well, in our case, it was flying creatures. So we implemented a simple implementation of aerodynamics that can run in real time. We essentially made an approximation of a flat plate, implemented the aerodynamics equations for that simplified scenario, and then we gathered the aerodynamics coefficients from papers in the literature that studied actual birds. So what we got was a body part that was simulating a plate-like wing, if you will. So with that, we constructed a flying creature and we just clicked the same button. What happened? Well, here you have it. So essentially we get real-time physics-based flying creatures for free with the same framework. And tell me that this is not some of the best animations that you have seen in Bird. And remember that it's running completely in real time and is completely interactive. If you were to throw a box at it, the bird would react physically. If you were to change the wind, the bird would also react physically to that change. Okay, so very good. Now our little girl is very happy. She can create a creature with the editor that we provide that hopefully is easy to use, and then she can just push a button and the creature comes to life. But soon she gets a bit bored, right? And she asks herself, can they do more than just walking? I mean, real creatures do not just walk from one place to the other, right? They also eat, they stand still, they can jump, they can perform a variety of tasks. So it comes to question high-level control. And how would we do this? Well, let's return to the sketch that I showed you for the brain. Essentially, it takes one observation and spits out one action. How would we modify this framework to account for high-level control for commands? For example, now walk and now stand still, or now jump. Well, the answer is disappointingly simple. You just modify it like this. You add together with the observation, you add a task observation, which at each point will dictate what task the creature is performing. And the task is defined by a reward. So if you wanted to walk at some time and you give the task observation, then you give the reward for walking. If then you switch to standing still, then you have to switch the reward to a reward that encourages to stand still. So we implemented it with something that we called reward modules, which would be like Lego blocks of reinforcement learning in this context. So each reward module would be a very basic reward that encourages the agent to do one particular thing. For example, the progress reward would be one reward that encourages progress towards a goal. Then you could have a module that penalizes for crashing and so on. Once that you have those modules, you can just stack them like Lego blocks, forming tasks. Each of these tasks, with different reward modules, would have a reward, which could just be the sum of the reward of each of the reward modules. In this way, we can craft tasks very easily, reusing the same reward modules. And we are also giving the future opportunity for users to even craft their own reward modules and tasks very easily. So let's see this in action. Let's see Lizzie walking just like before, but now also stopping. And you see that she stops in a very cute way, right? And we cannot really control how she's going to stop. We cannot control how she's going to move the tail, because Lizzie has decided to stop in some particular way. And this is another feature of this technology. You have to abandon the notion of complete control, and you have to delegate some small things, such as movement of the tail, to the creature. This is the biped, walking, but also standing still. You'll see that standing still, the biped learns how to stand still, minimizing the energy very efficiently. And also, we have crafted completely different tasks, such as jumping. Here, Lizzie has a hat because she's jumping, so she's Cowboy Lizzie. And now, let's put it all together and see Cowboy Lizzie perform a multitude of tasks with the same brain. Okay, and now another task that we can think of doing when we have the possibility to train to do multiple tasks is dancing. In my small dancing universe, dancing is basically a combination of two movements. Move right and move left. So What we did here is crafting those 2 tasks, and then once that we have trained, we can schedule them to the rhythm of the music and see what happens. And notice how the creatures, even though there's only 2 tasks, never perform them exactly in the same way, right? Some of them, the spinning were done like this, and some other times the creatures will do in this travolta move, and I didn't even program to do this. We're gaining some liveliness out of the unpredictability of how they will perform the tasks with only 2 of them, and that is worth noting. Okay, so good. Now our girl is super happy because she can, using the same framework, train the creatures to perform different tasks, train them to jump, to walk to different spots, even to dance. And now she wants them in the world. And to her surprise, when she deploys them into the world, then nothing works. They keep falling all the time. And of course, the problem is that the world is not flat. Who would have told us, right? We trained all of these creatures in one set of environments, while the real world, or our virtual world, could be different. And okay, so she says, there's no problem. I've been listening to Jorge for a while now, and he told me that I should just gather the information and I will just train them in some hills. And she does that, but then nothing works. They still keep falling all the time. And she can understand why I've been lying to her for almost, 40 minutes. And the reason is hard environments. We have to devise some way to deal with these hard environments. So let's take terrain as an example. As I told you, we can just take some observation relevant to the particular terrain and stack it in a list of numbers and pass it through the brain. Now the brain should be able to adapt to the specific terrain that the creature has. But if you just do this, then it works terribly bad. Because the creatures don't catch a break to learn anything. They keep falling from the beginning, and then they just keep falling because the task was just too hard to begin with. So there is a notion of curriculum that we humans use as well. It wouldn't be wise to teach kids to integrate before we teach them to sum, right? So we have a notion of learning something first easy and then hard. And interestingly, it's been proven that with reinforcement learning is the same. The way to learn a hard task is to learn first the easy tasks. And since we don't know how exactly define a priori how hard it is one task or how hard is another, I don't know if one mountain is harder for the creature than just a set of hills. We use an adaptive curriculum. So at every point in time, we give different environments to different creatures, and we estimate which ones of them are harder than the others, and we adapt the difficulty of all the tasks to be just right, to not be too easy and not too hard, so that they always keep learning. And the result is something like this. Creatures learn finally to handle terrain appropriately. We can see the hand walking in a hilly world, or we can see our biped skinned as a burger, which we call Burgerman for obvious reasons, walking in terrain. And I want you to notice what is going on here. It's a biped, which is inherently very unstable, and we're putting it in terrain, which is very hard by itself. Here are some more recording of our biped walking in actually hard terrain. Terrain which might be harder than the one that it was trained on. So far, the biped does very good, and it's actually quite impressive how the coordination to walk in terrain is working here. And then we can test it on even harder terrain that it was trained on. And we see that at some points the biped might fall, like now. We have to deal with this situation, we have to accept them, because the world is never going to look exactly like the environments that we train the creatures on. So sometimes they're going to fall. Even if it looks exactly the same, sometimes they might fall, and we have to embrace this as well. So this is pretty much as I wanted to tell you today. But I want to tell you now about how apply all of these techniques to a AAA game. In particular, how we apply them to our first AAA game, Arc Raiders. In this game, players have to cooperate essentially to bring down massive robots, of which some of them are controlled by these techniques that you have seen in this talk. Among them, Wasabi, for example. Meet Wasabi. Wasabi is a creature just like Lizzie. Is a set of primitives stuck together by physical joints. It's trained in the same way. It's also trained with rewards, and it's also trained with different tasks and with a curriculum. What changes only is that we fine-tuned all of this specifically for this anatomy, to make it look right, to make it look scary, to make it look threatening. And this is the result. A massive robot, threatening massive robots that you can interact with physically. Payback is coming, eventually. You want to see the eventually? Well, I encourage you to see the trailer. I'm going to show you a portion of the trailer which includes Wasabi, so that you can see Wasabi in action in the game.
You owe me one. Perfect. Let's do this.
New contact. Breaking orbit. Southern Rust Belt.
They will never stop coming.
Marks on screen. Calling for volunteers. Enlist. Resist.
Okay, so you saw already how users were interacting with this massive robots, right? They were using physical assets like ropes. In one part, you saw someone shoot a leg off the robot, and the robot physically still manages to deal with the situation, because it's one of the situations that we have trained Wasabi for. So we have all of these options and these emergent interactions to our disposal, thanks to doing the animation physically with these techniques. But of course, it's not all roses. There are challenges to this. And the biggest challenge, in my experience, is that of reward shaping. You might have something very specific in your mind when you want a creature to move. You might want a creature to move from one point to the other, but you might also want the creature to move in a threatening way. Of course, how do you measure how threatening something is? How do you put all of your thoughts in one numerical value that we call reward? So that is very challenging by itself. And then, of course, there are other challenges that we might think that we get the right reward from one task, and a creature surprises us completely with a different way to achieve the same task. And some other times it's the contrary. We didn't have the reward right in the first place, and the creature might fail to fulfill the task because of that. So here there's a set of examples of all of this. You see, in some of those, the bear was walking backwards because we misspecified the facing reward. In other one, Lizzie was becoming a biped and was leveraging that because it was convenient. And in another one, the biped was becoming a triped because we were misspecifying the crash condition that made it crash. So this is hard, and you should deal with that. So as a final remark, this technology offers us a great spread of possibilities in relationship to emergent interactions and immersion, and also a great generality when animating diverse creatures. But of course, we have to give up something, which is fine control. If for your application you really want a very big fine control on how the creatures move around and are animated, maybe this is not for you, because it's very hard to achieve that level of fine control. But if you're willing to allow for some emergence and some situations which are not explicitly programmed, then this might be for you. And I wouldn't want to finish this talk without giving credit to some of my colleagues that also make this possible. Riley was working with me in this area of diverse creatures very closely, and Aaron and Emil, even though they went for other adventures, they performed fantastic engineering job in all of this. And Jack and Martin were part of the research team as well with us that made this possible, but they focused a bit more in our creators. Tom did some fantastic software engineering to put all of this together, and also to Magnus as the head of research. And of course, it would be very hard to mention everyone involved in the project, right? But you know what? Here they are. I think there's nothing more satisfactory than showing admiration from a place where it's heard. And all of these people deserve credit because they're awesome. So, thank you very much for being with me in this talk, and have a great day.